We're going to spend a few minutes now talking about a law that might look familiar to you. We talked about a law in Physics 20 called Newton's law of universal gravitation. It was real similar in nature to Coulomb's law that we're going to start talking about now, including the way it was derived. There's an equation, or sorry, an experiment that was performed by a guy named Charles Augustin de Coulomb to derive a law that provides for us the relationship between electric force, the charges involved in that electric force, and the distance, as opposed to Newton, who derived a law that provided us with the relationship between gravitational force and masses and distance that separates masses. Here's what the experiment in both cases looks like in essence. You've got a top of a box. You've got a string hanging from the top of that box. You've got a rod on the end of that string, and you've got two objects, one on either end of that rod. One of those objects we'll call number 1. It has a charge on it, Q1. The other one we'll call nothing, because it doesn't really matter. It's essentially only there to balance out this rod, so in essence, so it doesn't tip over. We're going to bring another charge nearby. We're going to call that charge 2. As charge 2 gets nearby charge 1, there's going to be a force. It might be attraction or it might be repulsion, depending upon the nature of the charges. Regardless, this charge 1 and the rod and the string are going to twist a little bit. That's the torsional nature of this. We call this the torsion balance experiment or the twisting balance experiment. Coulomb would have measured the value of R being the separation distance between charge 1 and charge 2, how far apart they are. That would have been really, really easy to find. Charge 1 and charge 2, a little bit harder. In fact, he couldn't tell exactly what the values of those charges were. He had no way of measuring it. But he did indirectly manipulate the charges by touching them against neutral objects. If he has a charge of Q, what's the number? 10, 15, 0.2? I don't know. If he has a value of Q and he touches it against something that's neutral, then it becomes a half Q. And then if he touches a half Q against something that's neutral, it becomes a quarter Q. And then if he touches that against something that's neutral, it becomes an eighth Q. And so on and so on and so on. He's able to manipulate the value of Q1 and Q2 without really knowing what the values were to begin with, in coulombs at least. So he's manipulating R easily. He can measure that easily. He can manipulate Q1 and Q2. Doesn't know exactly what they are, but he knows what they're changing by, so that works. And finally, the force, the electric force of attraction or repulsion between these two charges, that's the toughest one. This is what he uses the twisting or the torsional properties of the string for. You guys have all been on a swing set before. You get on that swing set and you start twisting it around as much as you can because you want to let it go and start spinning around faster and faster and faster, right? You guys know what I'm talking about, right? Everybody's done that. You know intuitively, even if you don't know anything about formal physics, you know intuitively, even as a little kid, that the more you twist it, the harder it is to twist, the harder it is to turn, and the faster you'll go when you let it go. Okay, again, you don't have to have any formal physics training to know that. With a little bit of formal physics, we can establish, all right, you twist it this much, it must have required that much force. Or if you twist it that much, it must have required this much force. Oh, it twisted 3.2 degrees. That must have been 10 newtons. Oh, 6.1 degrees? Oh, that must have been 17.3 newtons. And so on and so on and so on. So Coulomb is able to measure the force by how much the string twists. Just like we can compare how much force we applied to the swing set by how much we twisted the swing set. It's kind of like a spring scale, right? Remember those old Newton scales, probably used in junior high school? Okay, you measure the value of the force by essentially how much the spring stretches. We're measuring the value of the force here by how much the string twists. All right, so he sets up 3 experiments. And in each of the experiments, he plots a graph. In each of those graphs, we have the manipulated variable on the x-axis and the responding variable on the y-axis. In the first one, the manipulated value would be Q1. The responding variable would be F, how much force was applied as a result of changing Q1. And the second one, Q2. Again, the responding variable, F. And the third one, the manipulated variable is R, the responding variable is F. What do you think the control variables would be here? If this was a lab, you're going to do a simulation lab on Wednesday, by the way. This question will become really relevant on that day. If this, right now, what we're doing right now, was a lab, and you remember when we did our first lab, I said, listen, I don't really care about a million control variables. List the important ones. If this was a lab, what would be the important one or ones that I would insist on you stating? What's one of them? The size of the balls wouldn't actually be that important. No, it wouldn't. You'd have to keep R the same. What else would you have to keep the same? Not the size of the charge, the size of the ball, but rather the charge of it. So in other words, we'd have to keep Q2 the same. Does that make sense? There's all kinds of things that we should keep constant, but there's really two that are critical that we held constant, and that's going to be R and Q2. When he does this experiment, he finds that he gets a graph that looks like this. That's a linear relationship. That means as Q1 goes up, F goes up. If Q doubles, F doubles. If Q goes down by a factor of 4, F goes down by a factor of 4. We say they're linearly related, or they're directly proportional. That's the symbol for directly proportional. As one goes up, the other one goes up proportionally. Now, in the next experiment, he manipulates Q2. What are the control variables in this one? Should be like crazy easy now. What do we got to keep the same? R value and Q1. Yeah, Q1. When we plot this graph, we get, once again, a straight line. That's a linear relationship. That means that as Q goes up, F goes up as well. They're linearly related. They're directly proportional. F is proportional to Q2. And finally, in the third one, we're manipulating R, the separation distance. We make the distance bigger or smaller, and we see how F responds to that. What do we got to keep constant this time? What can't we change? Q2 and Q1. The charge. F stands for force. Now, when we plot this graph, what do you think it's going to look like? As the distance gets bigger, the force is going to get smaller. The graph actually looks like this. Now, this shape of graph could lead us to an inverse relationship like this. Whoops. An inverse relationship like this. Or it could also lead us to an inverse square relationship like this. It's difficult to tell just by looking at the shape because they're almost the same. But as it turns out, it's the second one, the inverse square relationship. Now, Coulomb looked at all this and said, all right, if F is proportional to Q1, and it's proportional to Q2, and it's inversely proportional to the square of the distance, then F is equal to, right, it's related to this, it's equal to a constant times this. Now, this equation should look a little bit familiar to you. Where have you seen something like this before? We alluded to it earlier. Newton's law of universal gravitation. Do you remember Newton's law? F is equal to G m1 m2 over r squared. That describes the force of gravity as it relates to the masses and the distance that separates the masses versus the one we just derived, which relates the electric force to the separation distance and the charges, the magnitudes of the charges. I heard somebody say just a second ago, whisper, what's the constant? The value of G, if you remember from physics 20, the value of G is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. That's on your data sheet, so you don't have to memorize it. The value for K,
8.99 times 10.
yeah, you're right, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. We're going to compare these two laws in a couple of different ways. One, the basic structure of the equation. We call them both inverse square relationships because the force in both cases is inversely proportional to the square of the distance. As r goes up, F goes down in both cases. That's what they have in common. Question? Right here? Yes, that's okay. That's what they have in common. Now, what's different about these? Well, we know that gravity is always an blank force. It's always an attractive force. Gravity can't be repulsive. But the electric force can be attractive or repulsive. Tell me why the electric force can be either one, whereas gravity can only be a one, only attractive.
Gravity only goes down.
No?
Because the Earth is flat.
Yes. How many types of charges do you have? Positive and negative. 2. How many types of mass do you have? 1. It's positive mass, right? There's no such thing as negative mass. So if you had 2 different kinds of mass, then it would be conceivable that you would have a repulsive gravitational force, but you can't have that. So what do they have in common? They're both inverse square relationships. What separates them? Well, gravity is only an attractive force, whereas the electric force can be attractive or repulsive. What else is different about them? The magnitude. One of them is way bigger, under normal circumstances, way bigger than the other one. Which one do you think is the bigger force, gravity or the electric force? There are 4 fundamental forces in the universe. And in physics 20, we talk about all kinds of different forces. Friction, normal force, all these different forces, centripetal force. None of these are fundamental forces. They're all caused by something else. The 4 fundamental forces in the universe that lead to all of these other things like friction and normal force and so on are the gravitational force. That's fundamental. There's the electromagnetic force, and this electrostatic force is kind of part of that, the electromagnetic force. Then there's a strong nuclear force, which we briefly alluded to at the beginning of the unit, and the weak nuclear force. We'll talk about those in our last unit of Physics 30. These 2 forces are fundamental forces. They are absolutely fundamental forces as compared to most of the forces we talked about in Physics 20. One of them, all other things being equal, is usually much greater than the other one. You step off your desk. You're standing on the top of your desk, and you step off your desk. What happens to you? You fall. And we know we're going to fall. That's a certainty, right? Because we've seen it happen every single time we've tried. Every single time we take a pen and drop it, it falls to the ground. Gravity is a pretty big force, right? Gravity is a big enough force to cause anything in its presence to fall towards the ground. Gravity's got to be big, right? It is a trap. It is a trap. Now, in the grand scheme of things, it isn't really that big. The only reason why we notice that always is because the Earth is so heavy. No, that's not what I was going to say. It's so heavy. It's so massive. Right? It causes a big force of gravity because the Earth is so heavy. You don't need that big of a charge in order to cause that big of an electric force. Picture this. Okay, you jump off that desk. Gravity causes you to fall downwards, right? What causes you to stop? The ground, the normal force. But remember we said the normal force isn't a fundamental force? It's always caused by something. What caused you to stop? What are the little particles called that make up compounds that are in your body? Atoms. Atoms. And what are the nuclei? What's the charge of the nuclei of atoms? What's the charge? Positive, negative? or neutral? The nuclei are what? Positive, negative, or neutral? Positive. They're made up of protons and they're made up of neutrons, right? The neutrons don't have any charge, but the protons do, right? So the nuclei of all of your atoms are positively charged. What are the nuclei of the ground? Positive, negative, or neutral? The nuclei of the atoms in the ground are also positive. So when your atoms get closer and closer to the ground, what happens to the value of R, the separation distance, as your atoms get closer and closer to the ground atoms? R gets shorter, smaller. As R gets smaller, according to this equation, what happens to the value of F? It gets bigger, exponentially, right? As R goes down by a factor of 2, F goes up by a factor of 4. So that means the closer and closer and closer and closer you get to the Earth, the electrostatic force of repulsion is bigger. At some point, what's going to happen? That electrostatic force of repulsion is big enough to stop you. That's what the normal force is, the electrostatic force that stops you. Now, which is bigger? The force of gravity that brought you down to the Earth, or the electrostatic force that stopped you once gravity already brought you down? The electric force. Gravity is big enough to get you going. The electric force is big enough to stop you once you sped up to 5, 10, 20, 30, 40 meters per second, depending upon the height you jump from. That make sense? Now, what's the way of remembering which force is bigger? There's a nice little cheat on this. How are we going to remember that the electric force is bigger? You can study. Yes, you can study. But you can also look at this. Look at the constant. 6.67 times 10 to the minus 11. Look at this one. 8.99 times 10 to the 9. Like, which one's nearly always going to give you a bigger force? The one with the constant that's 10 to the 20 times bigger. Is that okay?